Hi, welcome to the help session. Today we're going to conceptually explore the concepts of orbits. So the first main idea to understand is that, one that I'm sure that everyone does, is that gravity pulls things together. So just like this person here that you have sitting on the surface, or this apple, the Earth is going to be always pulling towards them, or pulling them downwards towards the Earth. It's technically towards their mutual center of gravity, but since Earth is so much larger than, a single person or an apple, the center of gravity is going to be so heavily skewed towards Earth that it's correct to say that everything is being pulled down towards the Earth. And so the second idea is motion, and this is a pretty encompassing idea. So relative to the Earth, and since all velocity is relative, this person right here, this person is not really moving and is thus being pulled directly down towards the center of the Earth. Like we said, the mutual center of gravity. And so the person could absolutely jump upwards, but very quickly the Earth will be pulling them straight back down, just like the Earth always wants to do, since the Earth's pull is uniform and constant. And so you could certainly try and jump up, and if you were really, really adventurous, you could try and jump up out of the pull of the Earth, but that's pretty hard. And so if you're able to do that, let me know. It's almost impossible. I'm pretty sure impossible. So the one way that people have worked to overcome this is rockets and engines. So if you've ever watched a space shuttle launch, you'll see that you have there's a space shuttle. This is a bad drawing. NASA, and so there's a bunch of, and the thing flies up, and it goes to space, and there's the moon. You got a bunch of little, and it goes and lands on the moon. That's really what it does. It's huge rockets and engines that give us enough velocity to escape the Earth. But there's this other term where there's escape velocity, and then there's orbital velocity. Orbital velocity is the velocity you need to actually orbit the Earth. Well, what is orbits? Let's try and define that with vectors and this cannon. So imagine you have this cannon and it shoots a cannonball. So the cannonball, let's say right here, we're going to shoot it once, it's going to go to here. So that went, a couple hundred feet, I guess, in this weirdly scaled Earth, and then it stops, it hits the ground. It's unable to resist the pull of Earth towards the center of gravity, which is nearly at the center of the Earth. Let's say we upgraded the cannon and we added a little bit more thrust to it. So we dumped in some more gunpowder and made it sturdier so it could withstand the gunpowder, and we launched another cannonball. And it went even further. The reason it went further is that the gunpowder provided more thrust, which became more velocity, or a greater amount of velocity, to actually move it further. And so you could look at the idea of vectors. So you have the cannonball, which initially is moving that way. It's moving straight out. But the only reason that it comes down is because the Earth is actually pulling downwards like that, straight towards it. And so the vector that's created is the vector addition. So let's get another color. It's right here. That's what's created, because you have the first component, which is the linear part of it. So it moves straight out of the cannon, but then you have Earth, which is pulling down on it. And so the green one is Earth pulling down on it towards the center of the Earth. Blue one is the just thrust generated by the gunpowder, thus launching the cannonball out of the cannon. And the red vector is actually where it's going to go because of the combined forces of the pull and the thrust from the gunpowder. And so we can keep doing this. We can keep increasing the amount of gunpowder that we put into the cannon. We can keep making it shoot further and further until it eventually, reaches all the way around to half of the side of the Earth, or the other side of the Earth, and reaches all the way around to right back to the side of the cannon. Just plops down right there. Well, what if when we launched a rocket, we launched it with engines attached to the cannonball? So follow this crazy idea here for a second. If we were able to make it go fast enough, where in the scenario where we had it going straight out and then also being pulled in by the Earth, we're able to make this vector, or this velocity vector, so large that it actually can continually overcome the pull of the Earth. So we make it go all the way around. However, when it gets to the other side, it just keeps going. Just keeps going and going. Because remember, we had this cannonball here, except we attached rockets to it. So there's actually it's like that's a bad color to choose. There's actually rockets on it, and so it's creating a bunch of thrust. This is a rocket. There's engines, there's big rocket engines on it. It's like a jetpack, and it's pushing it all the way around the Earth, and it's just moving out forever. The speed that this would actually have to go would be roughly 17,000 miles per hour, but it's absolutely possible since we have satellites in the International Space Station that are in orbit around the Earth, and this is technically the concept that they use, where you have these initial cannonballs falling towards the Earth. You actually have, say, this cannonball, which has rockets on it, it's going continually around the Earth, falling around the Earth. You have the International Space Station falling around the space station, because like I said before, with this vector, is that here's the Earth, and it's moving outwards, but it's also being pulled down towards the Earth, and so the continual vector would just be around it, and it'll just keep moving and moving as long as it's able to maintain that velocity. And so this is really what orbits are. It's an object falling around the Earth at orbital velocity. Orbital velocity is 17,000 miles an hour. And you may be asking, well, why doesn't it just launch off? Like, why doesn't it go straight out? Well, firstly, because of the gravitational pull, and second, because it's not able to go the speed required to overcome the gravitational pull. So where it's being pulled down straight towards the Earth, if this velocity vector was big enough where it was actually going 25,000 miles per hour, well then, it would launch straight off. And anything in excess of 25,000 miles per hour launch straight out. That's how we have to actually get rockets off the Earth. We have to use engines to make them go 25,000 miles per hour, essentially straight up. There's a little bit of curvature in their launch patterns, but it's basically as direct a path away from the Earth as possible, and as fast as we can make them go to get them out of Earth's orbit, or to escape Earth's gravitational pull. And so you can kind of generalize this idea to the solar system. So in the center we obviously have the Sun, and then in the first planet we have Mercury, Venus, Earth, Mars. And so really what this is doing, what the Earth is doing, is it's moving straight outwards, ignoring its orbital path. It's not just randomly moving in an elliptical path around the Sun. It's actually just moving straight. But there's also this gravitational pull from the Sun that's causing it to move in this direction. You can sort of imagine if the Earth was here, it'd be like that, and still moving linearly, except that its path is being changed by the fact that the Sun is pulling at it gravitationally. This is really all orbits are. It's just falling around the Earth, like we were describing before. You fire the cannonball, it goes a little bit further, fire a little bit further, until you're able to get it to go fast enough, or 17,000 miles per hour, which is the orbital velocity. This is actually an approximation, so this is the orbital velocity that you'd have to be at roughly, I believe, 400 kilometers. I believe this is, how many miles? 240 miles. 240 miles up. And this is actually roughly where the space station is. And so the International Space Station is going roughly 17,000 miles per hour right now, which means that I believe it completes 15 orbits per day. Orbit a day, or an orbit every 90 minutes. So the velocities that we're dealing with here are very, very exaggerated in terms of just like compared to normal life, where we'd never go 25,000 miles an hour or 17,000 miles an hour. The Earth is traveling, I believe, like 30,000 miles per hour. Don't quote me on that. Maybe even more, some extreme number. But it's really just falling around the sun, because if the Earth wasn't moving, it had a linear velocity of 0, it would just move directly towards the sun, because that's the only thing that's pulling on it. And so we'd basically just be headed straight for the sun, and we'd probably be there in less than 10 minutes. It would happen pretty fast. So whatever initial velocity that the Earth had that caused it to move in that linear path away from the sun is what's actually giving us that elliptical orbit. And so that's really all you need to know about orbits, in at least a conceptual sense, where gravity is pulling the object towards you, but the object is actually just falling around the object it's being pulled towards. Okay, thank you for listening to this explanation. I'm sorry if it was confusing. If you have any questions, or anything was ambiguous, or I didn't cover anything, or you noticed an error, let me know, and I will do my best to correct it, or help you out, or try to explain it again. Yeah, so thank you for watching my video on orbits. See you later.